Hi folks, the old fossil here. Today's project is about an ultrasonic data link. I came across this little transducer. It's a HC-SR04. It has an ultrasonic receiver and transmitter right on the same little board, and I just had to try to build a data link with it. Now there's some good news and some bad news. It can be made to work, but the ultrasonic is kind of sensitive and finicky. It seemed like a good idea at the time, so we tried it. This is a copy of the data sheet for the little transducer board. Only has 4 pins, power, ground, trigger, pulse, and echo. The idea is you provide it with a little narrow 10 microsecond TTL compatible trigger pulse. There's some processing happens in the little chip, and it generates an exactly 8 cycles tone burst. And there's about a setup time of something like 500 microseconds before the echo line rises high. Now, it's pulse width modulated, so the narrowest this little pulse can be is about 200 microseconds when the reflecting target is only 2 inches away from the transmitter. On the other hand, this edge here moves all the way out. The farther away the reflection comes from, the longer the delay time is, until finally the echo line drops back. If there is no echo at all, there's a timeout here that goes out something like 90 milliseconds, not microseconds, which is equivalent to roughly 90 feet. It would be like 45 feet out and 45 feet back for a reflection, which is far longer than the powered little transmitter could actually produce an echo from that far away. So the echo pulse starts slightly after the trigger pulse and is of a width for anywhere from 200 microseconds to 90 milliseconds, depending upon when the echo is received. So this is how I set up the data transfer. The top line is if you put the trigger pulse in, the master generates a query pulse, the trigger pulse, and there's a long time period. If there's no reply, this escape time can be like up to 90 milliseconds, anything longer than 90 milliseconds, because that's the maximum pulse width. When there's an echo present, the two little boards kind of ping-pong back and forth. The master generates a query pulse. There's a delay before it reaches the slave. I'm calling the boards master and slave. This separation delay depends on how far away the slave actually is, and it can be long, it can be milliseconds. The sound travels about a foot per millisecond. But I put a delay in the actual slave code to let the spurious echoes ramble around and die like little ripples in a pond. And then basically, after that delay, depending upon the data, you make the delay a little bit longer or shorter, 1 and 0. So there's a data delay when it's 1, and no delay, data delay when it's 0. Now there's a transition to separation delay again before the echo gets back to the master. When the master receives the echo, it does not immediately retransmit the next query pulse. There's a delay in it also to let echoes and bad things die away. And the second query pulse goes out, separation delay, slave delay. In this case, the data delay is 1. In this case, data delay is 0. The corresponding received echo, or the signal from the slave received by the master, when the data is 1, the pulse width is this wide. When the data is 0, the pulse width is that wide. So that becomes just a regular pulse width modulated data train, and you ought to be able to make a regulation data link with it. Okay, so here's the setup. The towels are trying to keep down the spurious reflections. There was a lot of reflections. The big problem was the sensitivity. The little sponge is in front of the receiver, each one, so that it decreases the sensitivity. The breadboard is actually simple. The power is coming in the USB connector to the MetroMini at the bottom. The +5 and ground goes over to the bus of the breadboard, and then from there there's only 4 wires hooked up to the little sensor unit, the power, ground, and the trigger pulse and the receive. So not much to it. And in fact, here's the oscilloscope waveform. The trigger pulse is very narrow in this time scale. It might be hard to see up there. Here's the second one. Here's the received reply pulse, with the data 1 is long, with the data 0 is short. So it actually works. A couple of pages of the code itself. We'll give you a 5-second delay on each one, just so you can copy them if you want to. After the pin definition and setup, nothing special about that. The actual trigger pulse and the master over here, the digital write delay 5 microseconds, digital write low generates the query pulse. Both of the received routines are a falling edge detector. You read the receiver pin, and if it's high, you make this one high. If it's not, you make this one low, and at the end of it you make that one equal to this one, so that if this one's 0 and the one before is high, you do the receive pulse routine. Count pulses, reset it at less than 9. I was going to send 8-bit bytes, generate characters that way. Save the time of receipt just in case you need it. Generate the next query pulse. So here's the long delay. This is milliseconds. And then write delay low for the receive pulse. This is the trigger pulse from the master. Essentially the same thing in the slave. A falling edge detector and a reply pulse. The delay in the slave is a fixed number plus data times 5. These are all milliseconds, so it's a 5 milliseconds, 0 or 1. So the total delay in the slave is either 5 or 10 milliseconds. Then the same thing, write high, write low. And in this case, all I'm doing is just flipping the data. After you send the data pulse, you reverse data from 0 to 1, so that you can see the change. I didn't bother putting in all the loop synchronization stuff. This is the last code page. The little subroutine here is not actually used. Just the hello world message. Like I say, I was gonna send characters, but it works, but it's finicky enough. I didn't really think it was worth all the trouble of making a full-scale handshake loop out of it. This little routine over here checks the first 8 transmitted pulses and just gives you a serial printout. You can't really use serial very much, because the timing is fairly critical in the loop, and serial interferes with the timing. After having all these problems with it, I went and found the little parts. This is a ultrasonic receiver. This is an ultrasonic speaker transmitter, and the two of these are only $5, where the HC-SR04 is $4, so there's not a lot of difference there. But oh, by the way, for these, if you built it yourself, you need all the electronics to support it. Now, I thought the biggest problem seemed to be the sensitivity. The little board is designed to respond to very small echoes, so it's sensitive. If I could build an AGC preamp that kind of tuned down the gain so that the only thing that came through was the big blast coming back with the data link on it, it would probably eliminate a lot of those kind of problems. Now, after fiddling with this thing for a week, I'm kind of burnt out on ultrasonic, but you never know, it's going to keep eating at me. Maybe we'll do it again. There's still some advantages to ultrasonic. It's invisible. People can't hear it. It should work day or night because it's not going to be bothered by sun or reflections. And oh, by the way, there's still no wires and no other connections, so it's a genuine data link. Maybe there'll be another project in the future. Thanks for watching.